Hi everyone, I'm Pasalis Beis from University of Cyprus. I will talk about Anyplace 4.0, an IoT localization architecture. This is a joint collaboration with our colleagues from Alstom, Infosys, and the University of Pittsburgh. The motivation behind our work is the unprecedented demand for indoor space localization, navigation, and tracking in smart spaces. Let's see 3 real-life examples. In healthcare, we aim to integrate with a fleet of robots for the Endorse project in order to provide safe, efficient logistic applications in care homes. Some example includes carrying medical equipment, drugs, and guiding or giving assistance to patients. In situations like the current pandemic, minimizing the physical human interactions can be extremely helpful. We can also aid in emergency response by providing 3D localization and guidance to firefighters for the Last Fire project. The goal is to increase the fire safety before and during a fire outbreak in ro-ro cargo ships, which are vessels carrying wheeled cargo like cars or trucks. With Alstom, which is a rail manufacturer corporation that produces the Eurostar and the JV trains in Europe, but is also building a smart factory in India with Infosys, we aim to bring location awareness and asset tracking. This can enhance guidance, optimize routes, improve supply chains while minimizing warehouse running costs. This is the main focus of this work in terms of defining the data requirements. And now a quick introduction to Anyplace. It is an internet-based indoor navigation platform with a highly active open source community. It has an accuracy of less than 2 meters and has received multiple awards, including a 2014 Microsoft Research Award. It is based on crowdsourcing and fingerprinting principles. Over the years, we have accumulated more than 200,000 user interactions and more than 3,800 service activations. With our online modeling tool, one can upload a floor plan and annotate the building within a minute. And within an hour, one can offer indoor navigation and search for a 2,500 square meters indoor space. This is achieved with Anyplace Logger, which is a tool that constructs Wi-Fi fingerprints which are mapped into space. A fingerprint is a power measurement of received signal strength indicators. It is measured in decibel, it is low in power, and can be easily read with smartphones. With Wi-Fi mapping, we allow users to collect multiple fingerprints while walking in a straight line. Heat maps can guide them on the density of the fingerprint. Once mapping is done, it is uploaded to the server in an optimized format that we call a radio map. Then, we can use the radio maps to provide localization by comparing input fingerprints from a user's nearby access points. Without such input, other approaches perform poorly. Anyplace, however, is able to localize a user and provide navigation. To position a user, we have a variety of algorithms. Nearest neighbor returns the closest matched entry from the radio map. KNN takes the average of the K closest entries, and WKNN weights them by giving a lower weight to the entries that are further away from the user. Now let's see a real example where a user listens to access point 1 and access point 2. Those then are fed into an algorithm which are compared against the radio map, and then the position is estimated. Now let's see some of our shortcomings. Currently, it is not possible to run Anyplace on the edge. That is, single board, low-end devices with these architectures, limited CPUs, and main memory. Deployment is also somewhat complicated. We have Play framework with Scala that communicates with Couchbase on the backend and expects to find specific buckets and views. On the frontend, we have AngularJS with a bunch of compiler tools. We also have SSL encryption. Portability is also a bit cumbersome. Our frontend is not designed to run natively on main environments. Also, it is getting increasingly difficult to develop and maintain many clients. Given the explosion of IoT, it is only natural that we want to reach emerging IoT OSs like Android Things, Windows 10 for IoT, or robotic frameworks like the RobotOS, but also still support traditional desktop OSs like Mac, Windows, and Ubuntu. Now let's see some additional requirements specific to Alstom. Multiple smart buildings constitute a smart factory. A building has interconnected assets that are divided into tools, workers, and parts. We divide those assets based on some localization criteria. Given that power source is a major point of consideration, we have divided assets based on that. We have, for example, big trade parts like engines that do not have any power source whatsoever, tools like smartphones that rely on battery power, and vehicles like a forklift that we assume has a constant power source. We consider other factors as well, like the life cycle of an asset or its localization frequency requirements. Now an overview of our architecture. Our server has web controllers for serving radio maps, floor plans, and their tiles. It also offers OAuth authentication. It communicates with the data store for storing radio maps to the document store, sensor data streams to the spatiotemporal store, and other raw files like tiles to the file system. Server also exposes a RESTful API that is used by our frontend client. On our web client, Architect allows the modeling of buildings, creating points of interest and routes. Those can be displayed with the viewer. Also, the analytics component provides some heat maps that show Wi-Fi coverage, localization accuracy, access point location estimation, amongst others. The library component performs some caching to allow offline operations. It also has a logging and localization modules. It can be used to create different IoT clients like for RobotOS, Android, and Linux. With blue color, we can see the new components. Now let's dive into the first one, which is Docker. We automate single node deployments with Docker and orchestrate the whole process through Docker Compose. Users are only required to modify a single .env file. Code is initially pulled from our GitHub repository releases, which is compiled with Jenkins. Docker will then initialize the database by creating a root account, a resource-based account to securely access specific buckets, and then go and create some buckets and some views, and finally do some tuning. We also provide SSL encryption even in internal networks. We do this by creating on the fly a certificate authority based on the user's .env file. Then we create and sign a certificate. We then start our Play framework application, which can securely access the database and also utilize the SSL certificate. We persist any important data from the Docker container by mounting them to the host OS. Such data are the database internal structures, file system data such as floor plans or tiles, and other log data. In our cluster, for example, we use Let's Encrypt for SSL, since we're on the public domain, GlusterFS for the file system, and we provide load balancing and high availability with hub proxy. Now let's see library and clients. Anyplace core is a Java library with the main functionality of Anyplace. It has a caching mechanism and a modular design, which allows it to be used either as a command line interface or as a Gradle library. The command line tool allows an easy creation of clients, a support, or major OSs. Let's see an example of Linux. We set the algorithm, pick the Wi-Fi card, and then scan for fingerprints. Then we call the jar file and estimate our position. With minor modifications, this snippet can run on macOS as well. Settings are stored in user's home directory under Anyplace, similarly with Docker. This conveniently allows someone to set up the backend and the frontend in minutes for testing or development. In that folder, we store authentication keys, backend connection settings, and the local cache. Now on to the Android library. It has the Android-specific logic. For example, sensor data acquisition, OS permissions, threads, and in-application caching. We use this library to create a thin Android client. Let's have a look at a small code snippet. We initially get the backend settings like host and the port from the app preferences and the cache from the app's internal storage. Then we use a library to create a client and finally pass a built-in ID to fetch all of its floors. Now let's see the spatiotemporal store. InfluxDB is a time series store with a simple schema suited for raw IoT data. It supports temporal queries for fetching data only within a time range. For spatial queries, we've implemented endpoints for geometric fences. We support a fence either between a single point and a radius or between two different points. It also supports real-time visualizations and analytics and can be seamlessly integrated with tools like Grafana. Influx outperforms Couchbase by an almost an order of magnitude for data ingestion. Specifically, it is 7 times faster with 1 million entries. It also executes queries faster. For time-slice filters, it is 28% faster. For aggregation, it is more than 2 times faster. For fetching a specific table, it is 3.6 times faster. And for emitting all entries, it is still 20% faster. Now, let's see the last component, which is a document store. MongoDB is a lightweight document store able to run on the edge with as low as 1 GB of RAM. Therefore, it can scale from low-end single-board computers to high-end multi-node clusters. Currently, it coexists with Couchbase as we are still migrating some views, but eventually it will completely replace it. Now, on to some concluding remarks. Open source localization architectures remain an open problem. We aim to support many different technologies under the same roof with crowdsourcing and fingerprinting. We are also looking into infrastructure-free solutions. A promising approach is to use computer vision with real-time object detection for interlocalization. We are also considering map matching algorithms to improve accuracy by associating fingerprints with underlying topology graphs. This was Anyplace 4.0. Thank you.